Well, let's move on to slightly related subject of cosmic gamma ray bursts. You can think of them as supernovae deluxe, and they're a really interesting phenomenon that puzzled scientists for many, many years. So they're first discovered in 1970s by these Vela satellites. They were military satellites that were launched to look for gamma ray flashes from nuclear explosions on planet Earth to enforce the nuclear test ban treaty. And they've seen gamma ray flashes, all right, but they weren't coming from Soviet Union. They were coming from outer space. And after they assured themselves that indeed this has nothing to do with Earth and politics, but something in the universe, this was published. And nobody knew where these things are coming from. They've been studied for a long time with different space missions, like Compton Gamma Ray Observatory here. The problem was they don't last very long, second maybe, and they're gamma rays. As you probably remember, you cannot focus gamma rays because they're shorter wavelength than interlattice spacing for any terrestrial material. Now, if you could take neutronium and make mirrors of neutronium, that'll work, but we don't have that. And so gamma rays could not be easily focused, and only we could get very rough direction using all manner of tricks where the bursts are happening, maybe tens of degrees in uncertainty. There are way too many things in a circle that's tens of degrees. So you have no idea which one could have been. And this is what they look like. These are from detectors and satellites. Think of them as Geiger counters. And usually there is a pulse and there is a decay. Sometimes there are many, many pulses. They come in two varieties. There are short ones, which have hard X-ray spectra, somewhat longer ones, softer spectra. And typically, the overall flux per unit area integrated over a pulse is of the order 10 to the minus 6 ergs per square centimeter. Now, if you put them at cosmological distance, that will be gigaparsecs away, and that will be something like 10 to the 29 centimeters, 4 pi r squared, multiply with fluence, you find out that energies emitted, if they were isotropic, were beyond the order 10 to the 52, 10 to the 54 ergs. How does that compare with the rest mass of the sun? Let's do mc squared. What's the mass of the sun in grams? Anybody? Okay, 2 times 10 to the 33. What's the speed of light in CGS units? 3 times 10 to the 10. C squared will be 10 to the 21, 10 to the 30, yeah? That'll be 10 to the 54. So these things would correspond to annihilating entire star in a space of milliseconds. Well, it turns out that's not actually the case. They're beamed just like pulsars are beamed. But we didn't know that for a while. And again, same reasoning as before. Their short durations implied very small regions. So black bodies could not be that luminous at all. And so they had to be some sort of non-thermal mechanism. So for about 30 years, people didn't know what these things were. And the resolution came in 1997 with a satellite called BeppoSAX, which had hard X-ray camera. And they can actually take pictures of gamma ray bursts, but in hard X-rays, which we know how to focus. And so suddenly, it was possible to tell where they're within arc minutes, which is much, much easier. And that led to the discovery of the optical counterparts, then later radio. And once you have optical counterpart, you can take spectrum and try to figure out where it is. And we've done that. In fact, this was done right here at Caltech. And so established that gamma ray bursts are indeed at cosmological distances. They're not, say, neutron stars in the halo of the Milky Way, which was another possibility. There are all kinds of crazy theories. So 150 theories at one point, and if most one of them is right, so if 149 are wrong, 150 are probably wrong. Well, actually, it turns out some of the theories are kind of right on the money. And this is what it looks like. This is the actual sky survey picture, and then picture taken right after gamma ray burst happened, and you can see there is an extra star pointed by the arrow. And then they fade according to the power law. The physics of this is really well understood from synchrotron radiation theory and so on. And then when we looked where are they turn out to be in galaxies, all right? And they tend to like star-forming regions of galaxies. So they're related to star formation in some way. So that went well with models that said, well, they probably related to supernovae in some fashion, and now I think that's what's generally believed. And there are basically two possible mechanisms. One is you can take neutron binary or neutron black hole or black hole and white dwarf or something, merge them together. The release of that orbital kinetic energy can create a gamma ray burst. We now think that probably the short, hard variety of gamma ray bursts come from this mechanism. Another one is you have a massive star that explodes as a supernova, leaving a black hole remnant. But it's not so simple. The idea is that the collapsing core makes a black hole. There is conservation of angular momentum. You get an accretion disk inside the star, a really dense material, neutronium basically, that is now accreting onto that black hole. So as far as that stuff's concerned, star doesn't exist. Right? And because there is a spin axis and magnetic field involved, you generate a jet which drills through the star as it's exploding as a supernova. The shock waves of that collide with material outside, convert energy into gamma rays, and if we're looking from the right direction, we see a gamma ray burst. This has now been established with very high degree of confidence, and these things have been studied to a great extent. A lot of it happened here at Caltech. Actually, the most distant objects for which we're pretty sure we know how far they are in the universe are these, because they've seen what are likely gamma ray bursts from so-called population 3 stars in the early universe.